Okay, hello everybody. So I hope you stay well and safe at home at this critical time. And since all the courses for the remaining of this semester will be delivered online, so for mce566, our class, and the delivery methods is through the video recording. So in each week, you will receive a video record and for the lecturing. And I would like you to pay attention to that. Each video record may not necessarily contain just one part. It may be separated into several parts. For example, in today's class, we are going to have in total 4 parts of the videos, and each part will focus on a specific topic. So in today, the first part, we are going to talk about some reviews on what we have talked about in the previous classes. And the second part, we will use an examples to illustrate some theories we learned in this class. And the third part, we will talk about some new materials on the theories. And last part of the video, it will be also another examples talking about uh, doing some practice on the theories. Okay, so let's get started. Let's do a quick reviews on what we have talked about so far. Okay, so since it has been 2 weeks, so let's do a quick reviews on all the materials we talked about by today. Okay, so in this class we start with, if you still remember, with talking about some preliminary results on how to describe a point in the 3D space, and then how to describe a reference frames or a frames simply in the 3D space. Okay, and after that, we use this preliminary knowledge to talk about how to model the kinematics of the robotic manipulators. Okay, and so let's write it down here. So the first part we have talked about is what is the description of points and frames. And the second part is modeling of kinematics. Okay, so for the second part, it's very important for you to understand. One is how to attach reference frames. Okay, for the given robotic manipulators. Okay, and you have how many steps? You still remember 6 steps, right, to attach the frames. And the second point you need to be understanding is, based on the attached reference frame, you will be able to figure out what is the DH table. Okay, establish the DH table. And the last point is, you based on the DH table, you use a formula to derive the homogeneous transformation matrix. Okay, and after that, what we talk about how to solve the opposite of the kinematic modeling problem, is the inverse kinematics problem. Okay, and we mentioned that for this part of materials, we just need to focus on the examples I mentioned in the slides. Okay, because for the inverse kinematics problem, there's no systematic methods to solve the problems. Okay, so what we need to do is just focus on the examples we mentioned in the class. And after that, we move on to another topic is dynamics modeling. But before talking about the dynamics modeling, we also talk about some preliminary results, right? Is what is how to establish the relationship between the joint variables velocity and the tip point's velocity. Okay, and in that part we have a concept called Jacobian's matrix, right? So the Jacobian matrix will be used to connect, okay, the tip point's velocity, okay, with the joint variables velocity, okay. And for this part we have two sets of equations, okay. One set is for revolute joints, the other set is for prismatic joints, okay. So let me remind you where or what do I mean by two sets of equations. So let's go back to, so this slide is lecture 9 to 11. So in order to establish the Jacobian matrix, okay, so this is the first set of equations. For revolute joints you have, okay, this equation for calculating the angular velocity and this equation for calculating the linear velocity, okay. And another set, so these two equations is for prismatic joints, okay. Here, okay, let's go back to here. And after that we also talk about how to connect the relationship between the tip point force, okay. So if we use F, capital F, to denote the tip point force, how many force you apply to the tip point, and I want you to go back to calculate how much torque, let's say is tau, you need to generate at each joint, okay, motors, okay, in order to hold the robotic manipulator static, right, given the force F applied at the tip points. So in this case we also have the results that, okay, the force and torque relationship is also through a Jacobian, but it's a transpose, okay, of the Jacobian matrix, okay. And we also have a set of equations try to derive these results, okay. And let's go back to here, and the set of equations is given in also the slide 9 to 11. Okay, let's see what is the equation. So this is the set of equations, okay, helping us to derive the force relationship, okay. So and then after that, in the previous class we move on to the modeling of dynamics, okay. So for the model of dynamics, we first talk about how to derive the acceleration information of the joint variables, okay. And we also establish several equations, okay. So this is the first one, second one, and the third one. So the first one is essentially the same as the second one, or the second one here is essentially a special case of the first one. Okay, so the first one is trying to establish the acceleration information, okay, it's VQA, okay, using the velocity and acceleration informations of the point Q at another reference frames. Okay, and the last equation is trying to connect the angular accelerations. Okay, so based on this result in the last class, we try to establish the dynamics of the given robotic manipulators. Okay, so the key idea, let's do a quick review. So over here, the key idea of establishing the dynamics of robotic manipulator is as follows. Okay, so let's suppose we have given you a robotic manipulator for just for examples, okay, like this. So you have one joint, first joint, second joint, the third joint, okay, just for example. So the objectives of the dynamics model is trying to, okay, trying to what? Let's go back to the slides over here. Okay, so let's look at the objective. So the objective is trying to here consider the dynamics problem is trying to compute the torque that corresponds to a given trajectory of a robotic manipulators. Okay, so given these objectives, okay, you can see that we are trying to connect, okay, trying to calculate how much torque. Let's say this is tau 1, tau 2, tau 3. How much torque we need to generate for tau 1, tau 2, tau 3, okay, in order to make sure that, okay, so this manipulator will follow some desired trajectory, not static, but moving, okay, following some desired trajectories. So we can specify this trajectory as, okay, for example, so for the joint 1, we want it to follow the theta 1 trajectory, theta 1 dot, okay, or maybe even theta 1 double dot accelerations, okay. And theta 2, so given you theta 1 dot, theta 1 double dot, and also theta 2 position, velocity, acceleration, and position, theta 3 velocity, theta 3 dot, theta 3 double dot. Okay, so giving you all this information, theta 1 dot, theta 1 double dot, up to theta 3 dot, theta 3 double dot. Okay, we want to calculate, okay, how much torque tau 1, tau 3 we need to generate in order to follow these desired trajectories. Okay, so the idea here is that we are going to use the first methods we learned in the previous class is the Newton-Euler approximation methods. Okay, so we are going to use the, for example, the Newton's second law, F equals to ma, and also the Euler's formula is what is given here, is all the external moments summing up together will be equals to the inertia of the body times the angular velocity, acceleration, plus the angular acceleration cross product the inertia times the angular velocities. Okay, so we are going to, so the key idea is focus on these two formulas. Okay, so in this, based on this idea, what we need to do, the idea is that, okay, so we consider each of the link of this given robotic manipulator. Okay, so we will first derive, okay, so what is the linear, so consider this first link. For example, if you have the mass, center of mass given here, and the center of mass of the second link is given here, center of mass is given here. Okay, so the idea here is that we are going to find out how much force F1, okay, and how much inertias we have here, 2, F3 and 3. So okay, we have here, and then we can go back to recalculate, okay, how much torque you have to generate by the first joint and the second joint and the third joint in order to generate the external force, overall external force, capital F1, capital F2, and capital F3. Okay, so in order to get F1, F2, and F3, what we need to have is, of course, what is the accelerations, right? A1, A2, A3. Okay, so in order to obtain the acceleration A1, A2, A3, what we need to do is we need to evaluate what is the linear velocity, angular velocity, and linear velocity. Okay, and also the linear velocity of the center of the mass. Okay, 1. Okay, so in order to get all this, so this is omega 2 V2 VC2 omega 3 V3 VC3. Okay, so in order to get all these variables, we have established a set of equations over here. Okay, right, given here. Okay, so the first step, of course, to get all these variables is going through the forward iteration steps. Okay, so what we need to do is we start from the base frame, okay, going forward, going through this direction, and to calculate what is the angular velocity and linear velocity of each joint or each links. Okay, and so this is the outward iteration. Okay, and the reason of doing this outward iteration is that we are going to start from the base frame, and the base frame is linear velocity, and angular velocity is mostly given to you, already know. Again, they are mostly equals to 0. Okay, and the second step is the inverse step. So after you have all these variables, and after you have the accelerations A, okay, and then you can calculate what is the external summation of all the external force F1, N1, F2, N2, F3, N3. Okay, and after that we are going backwards. Okay, we haven't done yet, or we haven't calculated the torque tau 1, tau 2, tau 3 yet. And to calculate tau 1, tau 3, we're going backwards, or sometimes inwards. So sorry, this is out. So this is inwards. Okay. So for the inverse, we also establish another set of equations. Okay, so this is another set of equations here. Okay, so based on the summation of force you calculated from the previous steps. Okay, so then you can going backwards or going inwards to calculate how much force or how much moments you need to be generated for each of the joints. Okay, so this is what we have in the previous class. Going backwards. Okay, and the reason of going backward is that normally we will know, okay, at the tip, we start from the tip point, and we will know how much force, okay, will be generated from the tip points using some tip point force sensors. Okay, so this is what we have talked about in the previous class. Okay, and so in the next video, we are going to use an examples to show you, okay, and how we are going to apply, okay, this set of equations to solve a dynamics modeling problems. Okay, and this is an example we left in the previous class. Okay.